Today I'm going to talk about molecular dynamic simulation using LAMMPS. During this talk I will basically talk about the concept of molecular dynamics and give some examples and talk about LAMMPS. For this session I have the outline like this. So I will start the first part, give some introduction by and some definition about molecular dynamic simulations, then some examples from my previous work. The last part will be about LAMMP, how to compile LAMMP, how to run the simulation, and all the comments about LAMMPS. So just a few words about my previous project. Before joining Westgrid,
sorry, Ali, sorry to interrupt, but is it possible to make your slides full screen?
Yes.
Thank you.
So just a word about my previous project. Before joining Westgrid, I performed some molecular simulation. One of my projects was to develop a Monte Carlo code to study order-disorder transition in binary OLUs. Basically, we developed a code with Metropolis algorithm, which is based on the atom vacancy exchange. We start from an order system. We exchange the position between the atoms and the vacancy, and we do this for different steps. At the end, we end with a disorder system. From this simulation, we can extract migration energies and so on. Another project was about amorphous silica. So we started from silica. We hit the system to higher temperature. Then we quench the system very fast. Then we look at the properties of the silica as a function of time. Another project was about metallic systems. So I studied melting, crystallization, and solid-liquid interfaces. Later I will talk about this subject. Another subject was to apply external deformation, which are shear deformation on amorphous silica using molecular dynamic simulations. Now we start with the first part, which is introduction to molecular dynamic simulations. So the first question, why do we need simulations? So the obvious answer is we cannot do all experiments, because sometimes they are impossible to perform, sometimes they are too dangerous to perform, depending on which subject. Experiments are also expensive and time-consuming. To perform an experiment, you need to have many steps, prepare the samples, analyze, sometimes use the neutron diffraction and so on. So it's very expensive. And with experiments, sometimes it's blind and there are too many parameters we cannot control. When you do experiment, you don't have control of all parameters. So an alternative for this, we introduce simulations. Simulation can be considered as a bridge between theory and experiment. When you develop a theory, at some point you end up with a differential equation, for example. So you cannot solve analytically this equation, so you have to introduce numerical integration using simulations. So from theory, we can use simulation by integration, numerical integration, for example. Sometimes we do experiment and we want to understand what happened in the experiment. So we have to model the system using the simulation in order to understand the experiment. So simulation is a powerful tool. It can replace some experiment. It can provoke experiments. When you do simulation, sometimes you find something and you have to verify this using experiment. So with the simulation, we can explain and understand experimental data. Simulation can be also considered as to complete the theory. So what are the computer simulation? Computer simulation is a tool to get insight about the properties of materials at atomic or molecular level. Using simulation, so we deal with atoms and molecules, so we can know exactly how the atoms move and relate some macroscopic properties to them, to their motion. Computer simulation are used to predict or verify some experiments. As I said earlier, it's a bridge between theory and experiment, because it provides a numerical solution when the analytical ones are impossible. Simulations are used to resolve the behavior of the nature or physical world surrounding us on different time and length scale. Using simulation, we can understand what happens at very low, at different length scale. Simulation can be applied in many fields, for example, physics, applied physics, chemistry, materials, and engineering. In this picture, I presented the different levels of simulations. We start by quantum mechanics. Using first principle or ab initio simulation, we can use just few atoms, and the time scale and the length scale are very low. So we are speaking about femtoseconds to picoseconds in time. Then from this we can increase the length scale and go to micrometer, where we use molecular dynamic simulations. The advantage of using molecular dynamic simulations is we can use more atoms, basically from few hundreds to few millions. And from one domain to another domain, for example, if we start from quantum mechanics, we can compute some parameters that are used by molecular dynamic simulations. And from molecular dynamic simulation, we can determine some parameters that are used at mesoscale or macroscale simulation. For example, if we use finite element methods to solve some problem like dendrite growth, we need diffusion constant of the atoms which are determined using molecular dynamic simulations. Now, what is exactly molecular dynamic simulation? Molecular dynamic simulation is solution of Newton equations. So we have Newton equations. So we have the mass, the acceleration, and the forces. So we consider a set of n atoms or molecules. Then we solve the equation of motion using some algorithm. I will talk about this later. Then if we have potential we can derive the forces. When we have the force, we can compute the acceleration. If we have the acceleration, we can go back, define the velocities, and from the velocities we can define the position. So if we have the positions of atoms at different times, we have basically the trajectory of atoms. From this we can derive many macroscopic properties. So to compute the forces, as I said, we need the potential. For MD, we have to solve this equation, which is the equation of motion. This is an example of the potential used in molecular dynamic simulation. We don't have to use all these equations. Sometimes we use just the first term, which is Lennard-Jones, which is the simple potential to use. We use also Coulombic interactions, which are very expensive to compute, because they are long-range interactions. Depending on the system, you can use one or more of these terms. Of course, this is the simplest potential function. There are more complicated than this one. Now, to derive the equation of motion, we need an algorithm. One of the most algorithms used in molecular dynamics simulation is called the velocity variable algorithm. To derive this potential, we just take the position and use Taylor's expansion at time t plus delta t and time t minus delta t. So when you develop on Taylor's expansion, you get the first term is the position, the second term is related to velocity, the third term is related to acceleration. And from this we can, so the idea is when you have the position and the velocities at time t0, then using this equation, you can have the position at time t0 plus delta t. So how this algorithm works? So we said we need the forces. So from the potential, we compute the force, and if we have the force, we have the acceleration. If we have the acceleration, we use this Taylor's expansion. We can compute the position at time t plus delta t. We have already the initial velocities and positions. There is another algorithm which is similar to this one. It's called the leapfrog algorithm. So basically they are the same, except that one uses the velocities, the position at time t plus delta t, the other use the velocities at half time. There is another algorithm more complicated than the previous ones. It's called predictor-corrector algorithm. This algorithm works on two steps. The first step is called the predictor step. From the initial velocity, like the previous algorithm, we compute the acceleration using the force. From this, we can predict the position and the velocities. Now we have the predicted velocities and positions. Now we can then we can compute the corrected acceleration. From the force at time t plus delta t, we have the force, so we can compute the acceleration. So now we have two accelerations, the predicted one and the corrected one. We make the difference to get difference between the two acceleration. We use this error to correct the positions and the velocities. Now, if I want to summarize how an MD program works, so it works like this. It starts with a step called initialization. In this step, we need initial velocities, initial positions, and other parameters that are needed to start the simulation. We need configuration of atoms and so on, set time step and so on. Then we compute the forces using one of the previous algorithm I talked about. When we have the force, we can use this algorithm to compute to solve the equation of motion. So we have we determine the position and velocities at time t plus delta t. We start from 0. We add time delta t time step. So we have the positions and velocities at the next time. Then there is another step which is called sampling. In this step, we do many computations which are, for example, if you want to compute some properties and print them, or if you want to, for example, to save the trajectory and so on. Then we increase the time. So we have a computation at time t equals 0. Now we increase the time and do the same loop many times as we need. So at each iteration, we increase the time, and when the simulation we reach the maximum time we need, we end the simulations. So this slide is similar to the previous one, but just there is another way to look at things. So we start, we need initial configuration. Like in this figure, we have configuration of amorphous silica. So we need basically the atomic position, X, Y, and Z. We need the density and the box length and so on. There are other parameters, of course. We need also to start with initial velocities. So depending on the temperature the temperature of the simulation, for example, if you do simulation at 300 Kelvin, so you need to initialize the velocities to the, for example, how it works, we start with random velocities, then we use Maxwell-Boltzmann distribution to then rescale the velocities to have the average temperature equal to 300 Kelvin. We need also periodic boundary conditions. Periodic boundary conditions are used to replicate. So we do simulation using a small simulation box. But what happens, for example, if an atom goes to the border, and basically, if an atom moves out of the border, it comes from the other side. It's the only way to mimic an infinite system. We do simulation for a small system, but the system is considered using periodic boundary conditions is like an infinite system. The most important in MD simulation is the potential. All the parameters we determine from MD simulations are related to the potential. So each system uses an appropriate potential. For example, you cannot use Lennardons to describe, for example, silica. Another parameter to set is the time step. The time step should be the order of the atomic motion. So the time step should be very short. It cannot be very long, because if we use longer time step, we miss what happens between the two times. So the time step is in the order of 1 femto seconds. Another step is how to control the temperature. For this, we define the thermodynamic ensemble. There are different thermodynamic ensembles. I will talk about this in a moment. So I introduced already the periodic boundary condition. So periodic boundary condition consists on duplicating the simulation box in all directions. In this picture, we have the yellow box is the simulation box. So when one atom goes out of the box, it's replaced by another atom that comes from the opposite image. Periodic boundary conditions are used also for to compute the forces. To compute the forces, we define a sphere. So we consider all the particles surrounding one particular particle. So sometimes if we take an atom which is close to the border, so we have almost half of the sphere outside the box. So the particles from the opposite will replace this half, empty half. So for each atom, we have a complete sphere of atoms. Sometimes we use other boundary conditions. For example, in this case, if you want to apply external forces. For example, this example, shear deformations. So we define what is called fixed boundary conditions. So in this example, we have periodic boundary conditions in two directions, but in the third directions, we define two walls, two walls. So to apply the shear deformation, we apply forces in the opposite at each wall. So it's the only way to apply the shear deformation on this on any system. So I talked about thermodynamic ensembles. There are mainly three ensembles that are used. The first one is called NVA, or macrocanonical ensemble, where we have N is the number of particles, which is fixed. V is the volume of the system, which is fixed. E is energy. So for this system, we have constant number of particles, constant volume, and constant energy. Just to mention, for all MD simulations, we use always constant number of particles. If you want to change the number of particles, you have to do Monte Carlo simulation, because using Monte Carlo we can add atoms or remove atoms. Sometimes there are programs where we mix between Monte Carlo and MD simulations. Another ensemble is called NVT. So we have constant number of particles, constant volume, and constant temperature. And the third one is called NPT, or Grand Canonical Ensemble. We have constant number of particles, constant pressure, constant temperature. Constant pressure, for example, if you want to run simulation at pressure equals 0, or another pressure, so this is the system we use. Another ingredient, so we have to control the temperature. There are many ways to control the temperature. The easy way is velocity rescaling. So for example, you run the simulations for a few steps, then you, from the velocities you can compute the temperature of the system. Then you compare this to the temperature of the simulation used, then you rescale to change the velocities, then continue. There was also if we run simulation in MPT, so we have to control the pressure using some algorithms. There are many, for each algorithm there are many mathematical formulas, so I didn't add those. Now we have everything for an MD simulation. So we have a potential, we have algorithms to control the temperature, we have algorithms to integrate the equation of motions. So what can we compute using MD simulation? Basically, from MD simulation, you can compute every parameter that can be related to the positions or velocities or forces. So most physical properties can be related to atomic trajectories. By trajectory, we mean the atomic positions as a function of time. So there are, for example, some structural properties that can be computed. For example, a radial distribution function, which gives you the probability to find, for example, if you have two types of atoms, for example, the radial distribution function between A and B is the probability to find one atom B at a certain distance from an atom A. There are also dynamical properties. For example, the mean square displacement, which is the average of the displacements of atoms as a function of time. From the mean square displacement, we can also compute the transport coefficient, or the mass transport. These parameters are used by other simulations like phase field modeling. Now, these are the thermodynamic properties that can be computed from MD simulation. For example, kinetic energy, which is related to the velocities. Temperature of the system, which is we can just derive it from the kinetic energy. Configuration energy from the potential. We can compute the pressure using this relation, which so the pressure is related to the positions and the forces. We can also compute specific heat. But for this, we have to run the simulation using NVE system. Here I just put some example from structural properties. For example, this three figures are the radial distribution functions for aluminum nickel. We have here two compositions at two different temperatures. So the first peak, for example, gives you the probability to find, for example, aluminum atom starting from another atom nickel. So this is the first neighbor. Then the second peak corresponds to the second neighbor, and so on. We see that if you have a liquid, after 2 or 3 layers, the radial distribution function goes to 1, which is not the case if you have a crystal. You have many peaks. Another structural property is the structure factor. Structure factor can be determined using the experiment from X-ray or neutron diffraction. From simulation, we can compute radial distribution function, and we can just use Fourier transform to transform radial distribution function to structure factor. For the dynamic properties, I already told about mean square displacement. This is an example for the mean square displacement for aluminum nickel. So basically, if you have started with the fast regime for a short time, and then there are 2 or 3, 1 or 2 different regimes depending on temperature. If you are working at high temperature, so the diffusion is very fast. If you are working at low temperature, there is a kind of plateau. Especially if you work on glasses, this plateau is very long. This effect is known as cage effect. What happens that the particle cannot move. It spends more time in the cage formed by the surrounding atoms. After some time, it can escape and diffuses through the system. And the diffusion constant are determined from the linear regime using this formula. To know more about MD, there are some books. For example, the first one, R of Molecular Dynamic Simulation. You can have more details about all the algorithms I talked about. Now, how to perform an MD simulations. So to run an MD simulation, you need a program. So there are many softwares. There are some softwares which are open source or free access, like LAMMPS, CP2K, NIMD, GROMAX, and so on. There are others also. There are also some commercial softwares. You have to pay for that. So like Amber or something. You can also write your own code, homemade or private code using C, C++, Fortran, and so on. For all the softwares, you can always ask your support staff to install or customize the installation, or if you have a problem to run any simulation. Speaking of that, now with the new with Compute Canada, there are national teams. In this chart, there are many national teams. Just surrounded one, which is biomolecular simulation teams. The members of the groups of this group have expertise in one or two softwares I talked about. So if you have a problem with that, you can just ask them, and this is the link to the page. Now, before going further, is there any question from the audience? Is there any question? Okay, now in my previous slide, I talked about MD in general, so how it works, what we need. So we start from an initial configuration using, we have initial position and velocities, then integrate the equation of motion, then increase time and so on. So at the end we have trajectory or set of or atomic positions as a function of time. Then we can use this trajectory to compute some parameters. And for this, we have many programs, or you can write your own program. Now, in the next slide, I will give you some result. So I will start with the melting, crystallization, and solid-liquid interfaces in binary metallic systems. So why I choose this particular example? If you use a system with one component and you want to study the crystallization, basically you have just, for example, to go from the melt, from the liquid to solid state, you just quench the system very slowly. So you start from high temperature, which is liquid, then decrease the temperature and run the simulation and so on until at some point you go back to the crystal. But in the case of binary systems, this it's not working. So if you, for example, to obtain a liquid, we can start from the solid and increase temperature to obtain the liquid. But now if we just start from liquid and decrease temperature, at some point we will not get crystal. So how to study the crystallization in this case? So for this system, which we use MD simulation, we have a system of n particles. We use the velocity valid algorithm I talked about earlier. We use simulations at constant pressure, which is equal to 0. We use periodic boundary conditions in all dimensions, in all directions. So if we the first step is to study the pure phases, which means the crystal and the liquid separately, to have all the properties about this system. We can have, for example, lattice properties. We have the density, some structural properties, the diffusion, and so on. Then the second step, we use a system with two phases. In this picture, we have a system with the solid in the middle, which is a crystal, surrounded by the liquid. I will explain later how to prepare such system. So for this system, we use potential called EAM, embedded atom potential. This potential takes into account the electronic density, which is suitable for simulation in metals. So it's a potential with two-body interactions. It's considered many-body interaction because it takes into account electronic density. This particular potential reproduces the latest parameters and point defect in this system. So now to study the system with two phases, we take an elongated box in one direction. Then we have a system which is very long. Now, how to study the melting and crystallization? I talked about this earlier. So we start, for example, from a crystal, then increase temperature. At some point, the system goes to the liquid. we can continue on the liquid at a high temperature. Now, if we want to go back, so we decrease the temperature, we have almost the same path at a certain point, but we're around the melting point, we cannot go back to the crystal. Now the enthalpy of the system is higher. This system, here we obtain something which is called metallic glass. So this system cannot crystallize from the melt. So using this technique, we cannot define accurately the melting temperature. That's why we introduced this technique to have a system with two phases. So we have initially already crystal that so the system can grow from that. To prepare such system, we use an elongated simulation box. So now we fix in MD. It's possible to fix, for example, the position of a certain region of the simulation box. We fix those atoms as a crystal. Then we run MD at high temperature to have a liquid region. Then we quench the system to initial temperature. Now from this system, we can run different simulation at different temperatures, depending on the temperature. If we are, for example, at higher temperature, the system will melt completely. If we run the simulation very low temperature, the crystal can grow, and when we run such simulation, we print out the enthalpy of the system and the volume. From the enthalpy and the volume, we can extract the solid-liquid interface, solid-liquid interface velocity. Now, in this example, I have the same system at very high temperature. To characterize the system, I just computed the density. So what I did basically to divide the system into different bins along this direction, Z direction, which is the elongated one, in different bins. And for each bins, I calculate the particle density, which is the number of particles divided by the volume of the bin. So if I run the simulation at very low, at very high temperature, you see, for example, I don't know if you can see from here. We have a crystal at the beginning. When we run the simulation, after short time, the system became completely liquid, as we see from the last figure. Now it's completely liquid. Now if I do the same, but this time I will use very low temperature. So we have the crystal which is delimited by the red arrows. So if I run this same simulation for some time, we'll see that the width of the crystal increases, which means that the crystal grows. So this is a way to study the crystallization of such system. So after some time, all the system became crystal. And in this figure, from this figure also, we can see, for example, we started with a crystal just in the middle, but as we increase the time, the width of the crystal increases. If I let the simulation run longer, we will have all the system became crystal, like we started before melting. Now, using this technique, I missed one. Using this technique from the enthalpy variation as a function of time, from the last figure we have enthalpy as a function of time, we can determine the interface velocity. From this we have the melting point, the temperature at which the system became liquid. So this at this temperature, the liquid and the crystal coexist. For example, if I run this simulation at this temperature, 15, 18, so basically nothing happens. We have just some fluctuation around the interface. Some particles from the liquid became solid for some time, then go back to the liquid. Now, to understand more, we have to analyze the data. So the first analysis is this density profile. So we see from this picture that we have constant density in the liquid, and these peaks represent the crystal. Another parameter that can be used to characterize the system, we introduce an order parameter. So we compute this order parameter for each atom, and we make the average and represent this as a function of the distance, like density. We see that for the liquid we have constant order parameter, which is close to 0, and for the crystal we have the same envelope like particle density. Now, how to explain this? If you represent the interface velocity determined from the previous simulation, there is a maximum. So where this maximum come from? In this particular system, we have two atoms. So for example, if I take my data and divide all the data by the average diffusion constant, we see that this maximum disappears. So this maximum is related to the diffusion. Now, what happened when the system crystallized? In this picture, I just picked one particle from the liquid, then I tagged this particle to change the color to become red, that I can see how it moves during the simulations. For example, I start here. We see that in the liquid region, the movement of the particle is very fast. After some time, it approaches the solid-liquid interface, and the motion of this particle slows down. So from this, we can say that the crystallization depends on the diffusion of particles. In this system, we have two kinds of particles, so it depends on the diffusion of the first particle, the type of particles, the diffusion of the second type of particles, and in addition to this, compared to systems with one particle type, the particle has to find the right layer. So in this picture, just comparison between the diffusion profile and the density profile. So instead of computing the average diffusion over the whole system, I just divided the system for two small bins, like I did for the density, and computed diffusion of the particles that belong to this system. We see that when we are at a liquid, we have high diffusion. Then when we approach the solid-liquid interface, the diffusion slows down and goes to 0 in the crystal. So there is a theory that explains that relates the crystallization to the diffusion in the liquid phase, which is called Wilson-Frankel theory. But this theory cannot explain the crystallization of binary systems because it doesn't take into account the slowdown of diffusion at solid-liquid interface. Then we compare the data to experimental data. So in this case, they do experiment on microgravity. So they use plane, so parabola flight. So during, I think, 20 or 22 seconds, you have the gravity is equal to 0. So just the time to do the experiment. The blue point comes from experiment, and the black ones comes from simulations, and the red ones from experiment on Earth. We see that there is a shift between experiment on Earth and simulation. This can be explained by convection, but if you compare the blue and the black dot, we have a good agreement. Is there any question for this? Oh, it seems we don't have questions.
Ali, I do have two questions.
Yeah.
They came in through email, and sorry, since this topic area is not that familiar to me, I'm not sure if you've already covered this, but the first question is, how can you modify force fields, and do you need to install LAMMPS on a personal account for that?
For the potential, it depends on the system. So each system has, for each system we use a particular potential. There are, I will talk about this later, some potentials. For LAMMPS, it's possible to install it locally, but it's better to ask for support because they will install an optimized version. So like we did on Grex, we installed many versions that are accessible using a module. Just type module available, you see all the versions available from this software.
Okay. And so there's a second question. I've just typed it in the group chat because it's rather long and detailed. I didn't know if it's easy for you to see that, or would you like me to read it out? We should read out what you're answering for the web stream people, but if there are parts of it that you are going to cover later, maybe you can just touch on the ones that you haven't covered yet.
Related to the question before, is it possible to do umbrella sampling with LAMMPS? Yes, it's possible. There was...
Could you read out the question and... our people who are watching via web stream can't see the what's typed out in the group chat.
The question was related to the question before. Is it possible to do umbrella sampling with LAMMPS? I think it's possible. And the last one is, I'm also interested in simulating protein folding. Is that possible, easy or hard? Yeah, it's possible. To say easy or hard, it depends, because you have to set many parameters for the potential. So I'm not familiar with molecules, but definitely it's possible. But how hard it is, I don't know.
And there's one more question. They asked, it's related to QM-MM.
QM.
And they've asked, I saw that you can connect LAMMPS to other software. Is there a QM-MM option?
Yeah, I will talk about that later. LAMMPS is possible to couple this program to other. There is already this. You can also, for example, compile LAMMP as a library and call it from Python or from any other program. It's also coupled with few programs. We will talk about.
And one last one is it easy to load a PDB structure, for example, to LAMMPS, or is it hard and that's why people don't often use it?
Yeah, for the configuration, depends. Each software has its own, but it's always possible to go from one format to another, PDB to XYZ and so on. So for this, sometimes you can use some programs that convert one format to another, or just write a small one program that can read one format and transform to another format.
Okay, thank you.
Now we switch to another example. I already introduced shear deformations. So for this, we use amorphous silicon. So what we do, we start from an initial configuration, which is random configurations. Then we calibrate the system. We heat the system at very high temperature. Then quench the system very slowly to obtain an amorphous silicon. Then, before starting shear deformation, our system is already calibrated. Then we define two walls, upper wall and lower wall. To apply shear deformations, you have just to fix one and move the other wall in the opposite in one direction. So these are some results from this simulations. In this picture, I have plotted the potential energy difference. So energy potential minus energy potential before shear deformation. So as we move the wall, the energy potential increases. At some point, it breaks down because we reached already the elastic limit. Then the potential energy continues as a constant or fluctuating around some constant. Depending on the velocity used to move that wall, we have different behaviors. Now, if we do the same but at very slow velocity, we obtain the last figure, which corresponds to very slow. So we see that the maximum energy potential is dependent on the velocity used to move this wall. In the second plot, I just reproduced the maximum and the average energy potential when it's constant as a function of the shear velocity. We see that both properties follow the same behavior, which is a quadratic increase of the energy potential as a function of the strain. Now, the goal from this project is to characterize the defect under external deformation. So, for amorphous silicon, without applying shear deformation, we have something. Most of the atoms have a coordination number equal to 4. We have something like 97 or 98% of the atoms have a coordination number 4, and a very low amount of coordination 5. Now, when we apply the shear deformation, we see that the number of atoms that have 4 coordination number decreases, and then the opposite 5 coordination number increases. So, which means that increasing shear velocity leads to an increase of defect in the amorphous silicon, and a decrease of the number of atoms that have 4 coordination number. Now, if I do in the previous simulation, when we use, for example, a high shear velocity, we cannot see much because we don't give enough time to the system to relax. So the idea is to use a very low shear velocity. So we move the wall very slowly, but in this case, to reach the plastic deformation, we have to run a simulation for a long time. Now, if I apply the same shear deformation, but at different temperatures. From this plot, we see that if we do simulation at 300 Kelvin, we have an increase of the potential energy, then we reach the flow. Now, if I increase the temperature to 600, I see that the change is very low. So there is a small increase of the energy potential. Now, if I run the same simulation at 900 Kelvin, we see the opposite effect. So instead of increasing the potential energy, we have a decrease of potential energy. This is related that because there is some change in the phase of the system. This effect is more visible when we increase the temperature. For example, here at 1000 Kelvin, we see that when we apply shear deformation, the potential energy decreases. This means that the system starts to crystallize. Now, to analyze that, we use these are the small elements for crystal. So we analyze the structure of the system based on this. So we take for each atom, we look at the surrounding and compute the number of atoms that have this one or these two particular structures, which is related to the crystal. So in these pictures, for example, at 300, we have just few atoms that have surrounding, like in the crystal. When we go to 600, we have more. 900, we have more. And at 1000 Kelvin, we have almost maybe 90 or 80% of the system like crystal. We can also use the coordination number, count the number of atoms that have coordination number 4 to see that in this case how it changes as a function of the strain imposed. Another example is borosilicate glasses. These glasses are have three components. They have silica, borate, and sodium. So in my previous example, we have just used a system with two atoms. Here we have more. So using MD simulation, if you have a right potential, you can run simulation for a system with many atoms. So in this case, just how to I want just to show how to prepare a glass using simulation. It's like experiment. So, to prepare a glass experimentally, you have to mix all the components together. You obtain a powder, then you heat this powder at very high temperature to obtain the liquid, then let the system to cool down. At the end, you will get the glass. Numerically, or using molecular dynamics simulation, it's almost the same. So we start from an initial configuration, which is a random configuration, with according to the composition we want to simulate. Then we run the simulations at very high temperature. Here using NVT ensemble. At very high temperature, we obtain a liquid. Then we start to decrease the temperature step by step until we reach temperature 300 Kelvin, for example. Then before analyzing the glass, we have to equilibrate the system at this temperature. This time we use NPT ensemble at constant pressure to give a chance to the system to relax and obtain its own density. When you have from this simulation, you can compute the average value of density, then rescale the last configuration to this density. From this, you can start any simulation for a production run. So in this example, there is how to apply indentation. So you have your glass, you apply indentation. So what you need, you have simulation box. Here they used something like 2 million atoms. So there is a fixed layer for the lower, like in shear deformation, you have to fix the lower of the simulation box. We have 3 atoms, and at the top we have the indenter. So from here, the colors here are according to depending on the density, we have different color. So from this kind of simulation, so you have many parameters you can control, for example, the penetration depth, you can control the speed of indentation, and so on. So before going to next part, I would like to thank some people I worked before, from Germany, from France, from Quebec, and so on. Is there any question before I go to the next?
Just a reminder for those who are connected via video, if you have a question, you can unmute yourself by clicking the microphone and asking your question verbally. Or if you are watching via web stream, you can email your question to info@westgrid.ca, and we will read that out so that Ali can address it. Thanks. I've received no questions over email at the moment. So.
Okay, so we can continue with the next topic, which is to introduce lamps. So in my previous slides, I introduced MD in general, so what we need to run an MD simulations, starting from an initial configuration, initial position velocities around the simulation, and so on. So now there are a few softwares that perform MD simulation. One of them is LAMMPS. LAMMPS is an acronym of Large Scale Atomic Molecular Massively Parallel Simulator. This picture was taken from the LAMMPS website. Now, what is LAMMPS? So to learn more about LAMMPS, there was this homepage of LAMMPS. From this, you can find many useful informations. For example, to see what people have done using LAMMPS, there are some results. All the papers published using LAMMPS can be found on the website, on this link. There are some pictures and movies where you can see what people have done using LAMMPS. And to learn more, there is an online manual for LAMMPS. Basically, they have documented every command you can have with LAMMP. There is another source of information, which is the mailing list. Basically, people, when they have a question, they email they get answers. So before asking your questions, you can go to this mailing list. Your question may be already answered there. Now, where LAMMPS have been used. So, for example, you can use LAMMPS in biophysics, chemistry, granular flow, material science, solid mechanics. There are many examples on the website, so I didn't want to take everything. So next, I will just go through the LAMMPS website. From the LAMMPS website, there is a table at the beginning. From this table, you have access to different links. For example, if I take futures, so this will gives you what can you do and futures and non-futures, what can you do or what cannot be done using LAMMPS. There is also a link with where you can download the software, link to the publication manual and so on. There is another link, for example, with this one, workshops. If you follow this link, you will have access to the talks, for example, last workshops in 2015, I think. Just below this table, there is recent LAMMPS news. Whenever they add something to LAMMPS, they add it to this. For example, the last one added, it was on January 17. So fix something. So whenever there is something added to LAMMPS, they add it to this website. Now, how LAMMPS is designed? LAMMPS is free software. You don't have to pay or something. Just you have just to agree the license, which is GNU public license. So it's free to use. You can distribute it also. You can, if you are a good programmer, you can also modify it. When you modify LAMMPS, so you can even contact the developers if you can add that to the package. There is a manual how to develop something and integrate it to LAMMPS. So LAMMPS is written in C++. At the beginning, it was written in Fortran for a few years. Then they switched to C++. It's a parallel program using MPI. It runs also on GPU. To run parallel LAMMPS, we use commands through input script. So you have an input script, you write all the commands, and the LAMMPS will start the commands one by one. What is good with LAMMPS, it could be interfaced with other codes. For example, if you if you have another code and you want just to use LAMMPS to compute the forces or something, you can interface your code with LAMMPS, and you call LAMMPS to compute those forces and use them in your code. It's also possible to couple LAMMPS with Python, for example. So how to obtain LAMMPS? You have just to go to download page, download the code, and there are many possibilities. You can download the source code, download the Tarbal source code. You can also download the pre-built executable, which are RPM for Fedora, Red Hat, or CentOS, or OpenSUSE, depending on your environment. Another option is to install it on Windows. You have just it's an executable you download and you install it. But when you download, for example, RPMs or Windows installers, you don't have all the packages included. So So here from the download page, you have a possibility to download the previous version from 1999, 2001, and there is the second, it's development version. So the most recent version. But if you want a working version, you have just to download the first one, which is the stable version. The last one was made November 2016. So you download this, and so as I said before, so if you install from RPMs, you don't have all the packages that comes with LAMMPS. For a customized installation, you have to build from a source. So you have to download the tarball file and install from that. So just it's possible to use, for example, Windows installer. You can install it very quickly. So it generates some executable in this directory. From the when you install, you have access to the examples, and to execute LAMMPS, you have to go to that directory and use this. This is, for example, the executable LMP_serial.exe, and this is, for example, an input file. I will explain more about this later. So now. If we want to build LAMMPS using source code, so we have to download the tarball file. When you download, you will get a file called lamps-stable.tar.gz. You have to enter this file, and you will get directory lamps-17 November 16. This is depending on the version. If there is an update, you will have another name. Now, when you enter, you can go to the directory and see what is in the directory. In the directory, there are many subdirectories. There is a bench, which is the benchmark and test potential for LAMMPS. There is documentation where you can find the PDF file and HTML. From this, you have basically access to all the commands used in LAMMPS, even if you don't have access to internet. There is a directory example. There are more than 30 examples. These examples are very simple. You have already the input file and the output file. So to learn LAMMPS, the better starting point will be the example. Just go to the example and run them. You can run them. They don't take time, a few minutes or a few seconds maybe. There is another directory called library. If you want to build LAMMP, there are many libraries that can be used in LAMMP. But before building LAMMP, you have to build the library before. You have to compile the libraries before. There is another directory potentials. You have many potentials there. There is for Python how to use LAMMPS with Python. So if you have a Python program, you can just invoke Python LAMMPS from your Python program. There is a directory source, which contains basically all the source files in C++ and the include file.h, and there are subdirectories which correspond to packages that comes with LAMMPS, and user packages. User packages mainly the packages developed by other people. And of course, make files to build LAMMPS. There are some tools, like for example, there is a directory tools. In that directory, you can find, for example, Xmovie. Xmovie, it's like VMD, but just it works in 2 dimensions. Now, how to build LAMMPS? So, if you go to the directory library, you have all the libraries that you need to build this, to compile this library before building LAMMPS. Of course, you can you can compile LAMMPS without this library, but you have to remove the packages. I will explain how to remove any packages. So from this, you have, for example, if you need modified embedded atom potential for NetCDF, Python, and so on. So from the source file, I just explained there are all the settings, for example, make files, how to compile the source files, standard packages, and so on. So just to build, so you have to type make something. So to build LAMMP, we use make, GNU make. So if you type make in the source directory, you will get a message because you cannot build directly using make. There are some options. So the options are, I just put here some options. There are more. So for example, make clean all. So if you started already to build and you want to remove all the object files, just make clean all. For example, if you build with one machine corresponds, for example, if you compile, for example, OpenMP or MPI or something, so make clean MPI, it will remove the object related to this. To see all the packages with LAMMPS, just type make package to see to list all the packages. Now to see the status of the packages, to see if the package is already included or not. The make package status, it will list. If the package is installed, it will say installed. If it's not included, it will say not installed. If you want to remove any package, just type make no the name of this package. If you want to add the package, so make yes that package. Now to compile, we use make machine, and there are. If you go to the directory source make, there are many make files. So you have to pick one which corresponds to your environment. From that, for example, if I want to install LAMMPS on my laptop, I use here I use Cygwin. I just can make type make Cygwin. It will install. Of course, I may get some errors, so I have to change a little bit the make file. So if you compile correctly, you will get an executable. For example, LMP machine, depends on the make file you used. Now, how to run, we have already compiled and we have our executable. Now, how to run LAMMPS. To run LAMMPS, you need an input file. I will talk about the input file later. So you need also potential, because if it's start an empty simulation, you need potential that you can use to compute the forces. You need also an initial configurations. In LAMMPS, it's possible to read an initial configuration if you have already the file. The program can also generate some configuration. If you work, for example, if you want configuration with BCC or FCC or HCP or something, there is a very limited number of structures that can be generated using LAMMPS. Otherwise, you have to use another software to generate the initial configuration, or write your own program to generate your configuration, then adapt it to the LAMMPS format. Now to run this LAMMPS, just type your executable and add the input file. It's also there are two types. For example, I can use the first command or the second. LAMMPS accepts some command line options. For example, to introduce, to say to the program I want to use this file, so -en the name of the file. This is just, it's an interactive execution, but if you want to run this code on compute nodes, so you have to forward, because when you run, the program prints some data, so you have to redirect this data to another file, output file. So to run, I use LMP underscore machine, en LMP file, the input file, and this is the output file. So the command line options, there are many options. You can use, for example, -h to get for help to see how the program works. And you, for example, if you want to specify the input, so -i or -en, if you want to specify the log file, just -l, and so on. For example, to run the code using MPI, we just type MPI run -np 10. For example, here I just fix the number of processors to 10. The executor and the log file and the input file. It can be in any order. It doesn't matter if you use command line options. Now, how the simulation with LAMMPS works, we have basically 3 steps. So the first step is the input. So where you have to prepare your input file, initial positions, initial velocities, periodic boundary conditions, units, because in LAMMPS you can use different units. You have also to specify your potential and the ensemble you want to run the simulation. And of course, there are other options. Then you can run the simulation. So for the simulation, there are 3 different simulations using LAMMPS. You can run MD simulations, molecular dynamics. You can do also minimizations to minimize the forces of the structure. It's also possible to run a Monte Carlo simulation using LAMMPS. So when you run the simulations, the program depending on the commands you put in the input file, the program can print the trajectories, which means the positions as a function of time. You have to fix when you want to write the positions. You can print out the velocities, the forces, energy, temperature, many options. You can even add movies or a snapshot to the program. So how this input works? LAMMPS don't read all the input file at once. It starts from the first point, then continues. So there will be some order in the settings. For example, you cannot start by the command run if you don't have already all the input file needed to run the simulation. Because to run the simulation for n steps, we use the command run. Here, for example, you have to initialize the units, the dimension, etc., atomic position and velocities, interatomic potential, time step, because the time step will depend on the unit used, and you can change the time step depending on your system. You have also to fix the thermostat, how to control the temperature during the simulations, and there are some commands to compute some properties during the simulations. For example, if you want to add the pressure of the system as a function of time, you have to add that. The last step of in the input file is run. So there was a command run in steps. This will run. This means that the program will run for the indicated steps. Now this is an example of input file. 3D linear Jones melt. So you have basically just particles interacting via linear Jones potential. So there is a command unit linear Jones. There are other units also. You have to specify atom style with atomics, because there are also other atom style like bonds and so on. In this input, this region from lattice to mass, it's just the way to generate the initial configuration. As I told you before, that it's possible to use LAMMPS to generate the first configurations, but it's also possible to read the configuration for another file. There is a command to read that. To start a simulation, you need to generate the velocities. This command will generate the velocities. Velocity all create some parameters and argument. For example, if you restart the simulations, there was a way to read the restart file that contains the positions and the velocities. So in this case, you don't need to add this command, but you can also add it if you want to change the velocity. And the most important is the potential. For example, to add the potential in LAMMPS, it starts with the pair style. That tells the program to use this style or not. For example, linear Jones, embedded atom potential, or many others. Then you have to specify the parameters, the coefficient for the parameter. For example, here I have just one type of particle, so pair coefficients between atom 1 and atom 1 are those parameters. If you have, for example, two type of atoms, so you have here for mass you have 1 and 2, and for pair coefficient you will have 3, 1 1, 1 2, and 2 2. So depending on the how many particles you have, type of particles, you will change the potential. Another thing is the neighbor list. The neighbor list is used in MD simulations, so we don't have to compute all the pairs possible, because the interactions are limited to a certain point. So we prepare a neighbor list for each atom. It has some neighbors, so when we compute the forces, we just do the loop for the neighbors. And then once you have all these parameters set, now you have to fix which ensemble you use. For example, in this we have fix all NVE. So all the simulation will be in NVE ensemble. Then there are some commands. For example, damp. Damp here to store the trajectory. If I need to store the trajectory, I can add this command. If I don't need, if I just run an equilibration simulation, I don't need the trajectory, so I have just to remove it, because whenever you add something to the program, it takes more time to run. This is log.melt. As I said before, it's possible to specify the log file from outside, from command line, or it's possible to add it inside the input file. If you don't specify, by default, LAMMPS create a log file called log.lamps. Now, when you run the simulation, you want to check how the simulations runs and what are how the properties change as a function of time. For example, the pressure of the system, the temperature, and so on. So there is a command thermo, and the number of steps that says to the program how often to write these parameters. Then at the end, run. So run 250. This means that the simulation will run for 250 steps. So all the parameters on LAMMPS can be customized. You can change many things. For example, here for initialization, we use unit, boundary condition, atom style, and so on. For the force field, we use pair style, bond style, and so on. To define the atoms, so as I said, it's possible to read the data from restart file. If you have already the configuration, you can just read the configuration and start the simulation, or create the configuration using LAMMPS. There are some commands like this: region, create, atoms, and so on. Another possibility, if you start, for example, for a small simulation box and you want to generate a larger box, there is a command called replicate. This will replicate the small box in a different direction. You have just to specify the numbers, how to replicate the box. There are also, for force field, you have to specify pair coefficient and so on. For the simulation parameter, you have a neighbor list, run style, minimization style, and so on. Time step, you have always to set the time steps. Now, if you run in the same input, you can run multiple simulation, but it's not recommended, because whenever you run an empty steps, there are three different an empty simulation. There are three different steps. The first one is the preparation to prepare the simulation. The second is the running the simulation. The third is post-processing the data. Because, for example, if you run an empty simulation using NPT, this means that the density of the system will change as a function of time. Now, if you just take the last configuration and use it for another simulation without rescaling the density of the system to the mean density, this means that if you run the same input next time, the last configuration will be slightly different. You may get different result. So each time you run a simulation, you should post-process the data to understand correctly how things works. So during simulations, you can compute many parameters using thermostyle. By default, LAMMPS print out some parameters. I think time step, temperature, energy potential. But it's possible to change this behavior and print more data. Here I just have an output file. So, for example, if you run a simulation and you open the log file, it says, for example, I used here LAMMPS from July 30. I used 10 cores. In this file, the program writes also the command used in the input file, and some other comment. It says here created box and so on, created atoms, mass, and so on. Then the neighbor list. Then when the simulation starts, after when you write this command run, so the program starts to print out some data, thermodynamic properties data. By default, it writes the step, the temperature, the energy, total energy, and the pressure. But as I said, it's possible to add more this using thermostyle. Now the file continue at the end of the simulation. There are some statistics you can use. For example, here it says that loop time of 1549 seconds on 12 cores for 25 steps, 25,000 steps with 4,000 atoms. So from this you have you knew that this program takes this time to run this number of steps. So this information can be used to set the wall time for when you run your program. So if I have from this information, I can define, for example, if I run the simulation during 1 week, I can set the maximum number of steps according to this information. There is also other parameters which are the performance of your program. For example, in this table, it breaks down all the time consumed in different parts of the program. I just picked this example because it's very interesting. For example, these two red numbers. So the total wall time is 15 seconds with using 10 cores or 12. I see that the program spends 46% to compute the pair interactions. Usually in MD simulation, most of the time is spent in computing the interactions. And here, since I used an API program and the system is very small, so due to the communication between processors, so I have 44% of communication time, which is very high. So in MD simulation, we use this information to reduce. For example, for this system, it doesn't make sense to use 10 processors to run the simulation because the system is very small, so I can just use one processor and run the simulation. But if you use large systems with 1 million atoms, you will see that the communication time will be reduced. So this is how to modify the output file. For example, I talked about thermo. For example, if thermo frequency steps, you tell the program how often to write the output. Thermo style, you change. And there are many keywords, for example, steps, time, temperature, pressure, potential energy, total energy, enthalpy. Depending on your simulation. For example, if I run simulation in NVT, ensemble, or NVE, I don't need to print out the box length because they don't change. It's a simulation at constant volume, so the volume of the system or the density don't change. So I don't need to write this information because whenever you write something, you consume time. But for example, if I run a simulation in NPT ensemble, there are some other parameters I want to have. For example, in NPT simulation, the density of the system fluctuates, so I need this information to have the average density. So I can add, for example, the volume or density or the box length. Sometimes I want to have also the pressure, for example, in each direction, so I can add pxx, pyy, and so on. So depending on which simulation you are running, you can customize the output. So just a few minutes we have. So in LAMMPS there are many potentials. So there are some potentials for biomolecules like charm, amber. It supports those force field or interactions. Long-range interaction, Coulombic interactions. There are potentials for polymers. For materials, for metallic, we use more often embedded atom potential and modified atom potential, Buckingham, and so on, Stillinger, Weber, Tersov, and so on. There are also hybrid potential, for example, water on metals, polymers on semiconductors. So with LAMMP, it's possible to combine one or two different potentials. So this is the same slide as previous, but here the potential are classified by the functional form. So there are different types of potential. There are pairwise potentials. So the potential that defines the interaction between two atoms. Coulombic interactions. Many body potentials. So the interactions are computed using different many atoms, more than two. There are many methods to reduce the time. For example, I talked about the neighbor list. Since the interactions are limited to a certain cutoff, so we just compute the interaction inside the sphere. In some systems, it's possible, for example, to change. For example, we compute the interaction inside the sphere, and outside the sphere, we can consider the system as a continuum and replace it by, for example, the permittivity of the system, and the method is called the reaction-fed method. So it's a way to reduce the time consumed in computing the interactions. The interaction is the most important part in any MD simulation because it's the part that takes more time. So it can take more than 80% of the time. Now, to learn more about LAMMPS, the best start is to go to the website and see everything. You can also go to the examples and try to run. Most of them, except one or two, can be. It depends. For example, if the program is installed with all the packages, you can run all the examples. But for example, if I take Voronoi, for example, if you don't install this package, you cannot run this example. So to know more, there is also a list of papers published using LAMMPS. There are links to movies and pictures, and here on the website you can even find some input file that people published there. You can always use the online manual or on-site, and also subscribe to the mailing list. So I would like to thank LAMMPS developer for the time. Thanks also the LAMMPS contributors who wrote many packages and added them to LAMMPS. At the end of this slide, but I will not go over this. So I just added all the pair styles that can be used with LAMMPS. Thank you for your attention.